Dear Father, we thank you for this day again, Lord. I thank you for these students. I just pray you bless our time together. Help us to glorify you, Lord, in what we do. In my prayer, Lord Jesus. Amen. Okay, so I know at least one of you had a question about homework. So I will be happy to entertain that. Hopefully you won't ask me about one of the ones I'm stuck on. No, I'm just kidding. I know, it's calculus too. You never know. So which question was it you had a problem with?
68.
68 of what section?
So that's 8.3, number 88.
8.3, number 88. Okay. Was that your question as well? Which was your question? But you can give me in the book because unfortunately I don't have the right in front of me. 5.8, number 44. All right, her question's earlier in the book. I'll do that one first. We have time for more than one. Don't worry. Let's see here. 5.8, number 44. So we're supposed to integrate by substitution, or let's see here. So 44, we have the integral of the square root of x minus 2 over x plus 1. So we're supposed to somehow figure this one out by some sort of substitution. It gives us the u. Well, how insulting. Well, that's dumb. Let's let u equal x minus 2. Or how about x plus 1? That'd be better. Oh, wait a minute. Is that good? Oh, that's also bad. Curses. Oh, fine. I will take the insult. Square root of x minus 2. Let me try it. Assuming the book is reasonable. All right, so if we do that, then du is 1 over twice the square root of x minus 2 rather, dx, right? Which means that dx is equal to 2 square root of x minus 2 du, or in other words, dx is 2 u du. Do you guys so far agree? So this is what? This is really the integral. That's u. dx is 2 u du. And then I got this pesky x plus 1 down here, right? So if u is equal to the square root of x minus 2, then u squared is x minus 2. Therefore, x plus 1 equals what? U squared plus 3? Yeah. So this is apparently u squared plus 3. All right? So that is the integral of twice u squared du over u squared plus 3. How do we do this integral? You got choices. You could do long division, or you could use a trick. I'm going to use a trick if you guys don't mind. I'm going to rewrite this as 2 times u squared plus 3 minus 6 times du. See what I did? I added and subtracted 6. Why did I do that? Because with that, it's clear that this is the integral of 2 minus 6 over u squared plus 3. Now I know how to integrate 2, right? That's easy. So I get 2u minus 6 times the integral of du over u squared plus 3. This is a great chance for us to, we've got 2 different ways we can go here. You can look up the arctangent integral in that section. But since we know better and we kind of like need more practice, let's do a trig substitution here. Let's do this with a trig substitution. What trig substitution should you use here if you want to go that way? How about u equals the square root of 3, what? Tangent, secant, sine, which one? Tangent, right. Square root of 3 tangent theta. That ought to do pretty nicely. So this is all just for, to go up here really. Sorry. Okay, so if I do that, of course, du is root 3 secant squared theta d theta. U squared plus 3 is going to work out to 3 secant squared theta for the usual reasons. And so we have twice u minus 6 times the integral of square root of 3 secant squared theta d theta divided by 3 secant squared theta. Yay, secant squared cancels, right? And we're just left with integral of d theta divided by 3, so we get 2u minus 6 over 3 is 2, so 2 square root of 3 theta plus a constant. But of course I need to unsubstitute, right? So we got to go back to x's. What is theta? So let's see here. From this I can see that theta is inverse tangent of u over root 3, right? But what's u? Square root of x minus 2, right? Divided by 3. Okay, so let's put all the pieces together. What's the answer here? 2 times the square root of x minus 2 minus 2 root 3 inverse tangent of square root of x minus 2 over 3. Of course, plus a constant. Don't forget a constant. Wouldn't want to do that. Wouldn't be prudent. There we go. Now that's an integral. Thank you for this question. That one was fun. Yeah.
How come the square root of 3 is 3?
I'm sorry?
Like from 10, how come the square root of 3 is 1 to 3?
Oh, that's a good question. The answer is it's still in my blue marker. So, got me. Thank you. Yeah, there's no good reason for it. Just trying to make sure you guys are paying attention. Mission accomplished. No, that was a mistake. Anyway, yeah.
So I did this one by squaring both the numerator and the denominator, and then doing it that way. And
Whoa. I mean, what do you mean by just, you can't just square numerator and denominator. This is no allowed. What?
So I went square root of x minus 2 squared over x plus 1 squared.
But that's a different thing, right? I mean, like 3/5 is not equal to 9/25, right? I mean, we can't.
I see, okay.
I mean, this is, if I could do that, that would be really neat. Unfortunately, it's not allowed. But I see how would you, I mean, if that was an allowed step of integration, that makes total sense what you did, yeah. But no, we're not allowed. Sorry.
Okay.
There are places where we square integrals, but not like that. So don't give up on that idea entirely, just not like that. Yeah. Uh-huh.
So if we just use long division, we wouldn't have to figure out the fraction rate of.
Oh, yeah. Well, yeah, I mean, long division looks like this. 2u squared, what is it? 2u squared divided by, how'd it go here? U squared plus 3, right? So I go 2. And that brings me to u squared plus 6, and then I'm like minus 6. I'm like, oh, okay, done. So then that shows me that 2u squared over u squared plus 3 is equal to 2 minus 6 over u squared plus 3. So, I mean, whatever floats your boat. I mean, it's all good. We need something to address the problem, though, because if you just try to willy-nilly integrate things that have the same degree top and bottom, I mean, it can be done. I think probably could do that whole integral using the tangent substitution that I did. But it's so much easier to do the algebra and integrate too. Yeah. So. So your question was?
Problem 68, it's 8.3, number 88.
Say again, section?
8.3, number 88.
8.3, number 88. I'll take a look at that one. Whoa. Great. Googly moogly. Yeah. All right. Ooh, these are, it stinks that these are only from 0 to pi over 2, right? I'm just going to focus on A. I mean, I will foolishly attempt to do A with you guys. 0 to pi over 2. The nth power of cosine. Allegedly, we can show for n greater than or equal to 3 odd. In other words, n equals to like 3 or 5 or 7 or so forth and so on. We have the following formula. The integral from 0 to pi over 2, cosine to the n of x, is 2/3 times 4/5. 4/5 times 6/7 times n minus 1 over n. And we're supposed to do, how are we supposed to do this? We're given further instruction, right?
I believe you're using the formula in problem number 80.
Yeah, problem number 80. Cool. What is that? Let's see here. Number 80. See, part of the reason I assigned this is because I wanted to talk about these, and life got in the way of doing it up to this point. But one of the things we learned in problem 80 is, in number 80 in particular, we learned that the integral of cosine to the n of x dx is equal to cosine the n minus 1 of x sine of x divided by n plus n minus 1 over n, right? Integral cosine n minus 2 of x dx. So this is the so-called reduction formula for cosine. In number 79, 80, 81, and 82, oh, look at that. See that 82 right there? That's a reduction formula for secant. It's got a formula for secant to the n of x. That actually would be an efficient way to tackle those higher secant powers we ran into the other day with my unfortunate examples like yesterday, right? I don't want to get into it, but how about this one? So how does that help us with this? How does this number 80? By the way you prove this, you just do integration by parts, pretty much, right? If you do integration by parts on this, you can get that formula. It's not that hard, really, right? Okay, so we're trying to, the question is, why is this true, right? So I'll start out, integral from 0 to pi over 2, cosine n of x dx, right? Now that's equal to this. So we've got cosine of n minus 1 x sine of x divided by n. We have to evaluate from 0 to pi over 2, right? Definite integral. And then what? Plus n minus 1 over n. Look at that. That familiar? That factor look like anything we're looking for? Surely does, doesn't it? And cosine n minus 2 of x dx. So what happens to the term in the front? Plug in 0, you got sine of 0, which is 0, right? Plug in pi over 2. What's cosine of pi over 2? 0. So cosine to the n minus 1, that's just 0 raised to the n minus 1. So it's still 0. This term is kaput. It goes to 0. And so we're just left with n minus 1 over n integral. And I forgot my bounds. 0 to pi over 2 cosine n minus 2 of x dx. So then what do? We apply the recursion relation again. But here n minus 2 is playing the role of n, right? If you have trouble sort of overloading operators, it might be helpful to write this formula again with a different letter. So this is cosine to the k of x dx equals to cosine k minus 1 of x sine x over k plus k minus 1 over k integral cosine k minus 2 of x dx. So I'm gonna put k equal to n minus 2. All right? Make that substitution. In the result from number 80, what happens? We get n minus 2 minus 1, n minus 3 over n minus 2 integral of 0 to pi over 2 cosine n minus 4 of x dx. The term, cosine to the k minus 3 of x, n minus 3, x sine x over n minus 2 evaluated from 0 to pi over 2 is what? 0 again. So the first part of the formula in every application just drops out because we're integrating from 0 to pi over 2. And it just leaves us with the next power down, right? This is going to, so you see the pattern, right? So you go, aha, I see what's going on here. So what we're going to have is n minus 1 over n, right? N minus 3 over n minus 2, and so forth and so on the line until we get to what? How low can we go? N is odd. This is where n being odd is important, right? And did I say 3? Could n be 3? Is that right? Or did he say strictly greater than 3? N greater than or equal to 3. Okay. Let's see here. So when we get to n equals to 5, right? What happens with n equals to 5? Maybe I should say, trying to think here. Let me do the one before the last step. The one before the last step would be cosine to the, cosine to the 5th of x dx, right? What would we have had, what would be the thing in front of that then? We get to that stage. What's the coefficient? It's one more than what's here. N minus 3 versus n minus 4, right? So if that's 5, that makes this 6. That's the pattern. And if that is 6, then the one below is what? Right. Wait a minute. 7, yeah. Phew, that's a relief because we were looking to get 6/7 in here, right? So then the question is, where does the 4/5 come from? So what's the next thing past this? So then we get what? 0 to pi over 2? Cosine cubed of x dx, right? And what's here now? 4 what? Fifths, right? And then finally, what's the what comes next? Sorry, I think I wrote too many steps down. Maybe not, I don't know. Every step I'm using that the first term in the recursion relation formula from problem 80 drops out because we're evaluating from 0 to pi. So this is 1, right? So that's 1. That makes this, what, 2/3? Right? So what should we hope that this is? If Wallis' formula is going to be right. I mean, we already got the n minus 1 over n over here. They just ended up, I mean, what should this be? If that needs to be 1. If that's 1, we're done. Is this 1? Integral of cosine? Sine? Sine, evaluate sine from 0 to pi over 2. Sine of 0, 0. Sine of pi over 2, 1. That works out to 1. That's it. So, I mean, yeah, this problem looks imposing, but actually if you follow the advice of the textbook, it's just kind of one step at a time, you know? These can be very useful. Let me actually just pause here for a minute to see if we can derive number 80. That's actually a good problem for us to work. I wanted to work it. I was planning to do that like on the party day, but then, you know, we had to party, so what can I say? My claim was that we can get this from integration by parts. Can you, am I right? Am I wrong? How would we do integration by parts? Maybe here. I might be wrong. I don't know. I mean, my tendency here would be to rewrite this as the integral of cosine n minus 1 of x, cosine of x dx, right? If I do that, I can think of the cosine x dx as being the dv, and I can think of the cosine n minus 1 as being the u, right? I can do that. And if I do that, I won't get that n. Huh. Well, I guess that doesn't do it. I mean, look what, let me just try it. See what it takes us to do it. So this u is that, what's v? Negative sign? Okay, so, yeah, so. Why did I put a minus here? What? Oh, because I was thinking, I asked you guys what the integral was. I did it in my head. I put the minus here, and then forgot that I'd already done. Just one minus from the integral of cosine. Wait a minute. Wait, hold on a second. There's no minus there, right? What's the integral of cosine? You got me. You guys got me. Now maybe I asked what the derivative was. I don't know.
Oh,
It's been so long ago. Who can say what I asked? And then so minus the integral of v to u, right? Which is going to be, what's that, sine of x, and what's the du? Oh, now there's where the fun is. So what is, if this is u, if u equals cosine to the n minus 1, what's du? Differentiate cosine to the n minus 1 of x. What does that equal to? N minus 1, right? Cosine n minus 2 of x times what? Now there's a minus. So that's the derivative of cosine to the n minus 1 power. We have the n minus 1 function, the outer function, chain rule, multiplied by derivative of the inside function gives us minus sine x. So that gives us that beastly thing. So we get n minus 1 cosine to the n minus 2 of x sine of x, yowzers, dx. And I'm going to bring that minus out here and make this a plus. Okay, I'm not giving up just yet. This actually is what? What do we got here? We've got minus the integral of cosine n minus 2 of x dx, right? Oh, I'm sorry, I missed a what? So I'm thinking, sorry guys, let me stick just a second here. Let me clean this up. This is sine times sine. What's sine times sine? Cosine, sine squared, right? But sine squared x is what? 1 minus cosine squared. So this is really 1 minus cosine squared x, right? That's my sine. And then I've got my cosine n minus 2 of x, right? The n minus cosine n minus 2 of x. And then dx, right? And there's also this pesky n minus 1 factor, which I'm going to pull out front, if you don't mind. So what do you get here? You get cosine n minus 1 of x, sine of x. And then if you look at that, we have what? We have minus n times the integral of cosine n of x dx. Oh, I'm wrong. What do we actually have? So check it out. There's this n minus 1 here, right? So n minus, see, the cosine squared times cosine n minus 2 gives me cosine n of x dx, like that. Right? And what else is left? The n minus 1 times 1, right? So plus n minus 1 integral of cosine n minus 2 of x dx. You're like, wait a minute, that's not the formula we want. Well, that's true, but what could you see how that gives us what we want? Let me show you what we got. Call this thing I, right? What we have, the formula here is I is equal to this term. This right here is what? N minus 1 times I, right? That looped back to where we started. And then I've got this other term over here. Take this equation, solve for I. How do you do that? Add, this is actually a minus, n minus 1. So if we add n minus 1 copies of the integral to both sides, what does that give us? That gives us ni equals to cosine n minus 1 of x sine of x plus n minus 1 integral of the cosine of n minus 2 of x dx. So then what do you got to do? Divide by n. And that's exactly this formula up here. See, it's not this that appears in the formula, it's this divided by n. It's not n minus 1 that appears in the formula, it's n minus 1 divided by n. That n is coming from the looping of the integral and then solving for the original integral. So it is what I said. We just integrate by parts to derive that formula. Not uncommon to see derive this formula by integration by parts on a Calc 2 test. Not at all uncommon. Sperano asks that pretty often. Of course, these formulas are more near and dear to Sperano's heart than mine. I like just taking sine to the fifth and smashing it apart until it becomes integrals of, like, 1 minus cosine squared times sine x dx, and that way we did. Should I show you how this works? Let me just... So with this formula, if we want to integrate cosine cubed of x, how do we do it? If you know this, you'd say, oh, okay, well, that's cosine what? Cosine squared sine x, right? Divided by what? Here n equals to 3, right? Minus the integral of what? Oh, I'm sorry, I forgot my factor. Worked so hard to derive it, now I didn't even put it down. I'm supposed to put n minus 1 over n, right? Which is 2/3 integral of cosine. Yeah. And so there you go. This is the formula. I mean, obviously, this is faster than what I taught you guys, isn't it? Way faster, isn't it? Why don't I teach this? Why don't I make this the dominant thing I teach you guys? Do you know why? It's not an accident. It's not like I'm just learning this. I know about these. It's purposeful. It's because I think you guys need to learn about how to use sine squared plus cosine squared to manipulate expressions. If I make you memorize this recursion formula, sure, it allows you to solve this problem way fast, right? But it doesn't deepen your knowledge of sine and cosine like the way we did does. That's why. Now, if you want to memorize the recursion formulas that are given in the book on pages 79 through 81, you're welcome to do it. They will get you out of various dark alleys that you might run into if you make the wrong substitution or something. They are tools. Yeah.
How similar are these practice tests on the website to the tests that we see?
Oh, I don't know. I mean, you should try to do the homework and understand as much as you can of it. I don't think we can make any direct comparison because I've made a promise to make 50% of your test what? Like the homework, yeah. I don't usually make that promise. So.
Is that like a math joke with the series comparison by comparison? Is that like a comparison?
There may be a joke in there, but it was unintentional. Those are the best kind. Do you guys have other homework questions? Yes, go for it.
Section 5, number 78.
Number what?
Number 78.
78, okay. I will try to be helpful. Well, this is very exciting. I had prepared something to show you guys today, but I don't think I'm going to have time because we have all these questions, which is awesome. Now, I will get to partial fractions eventually today, but I'm probably just going to give you a handout, which is fine. So where was I? 5.8. A blast from the past. Let's see here. I mean, it's all the same stuff. Where are we? Number 78. Oh, that one's hard, isn't it? That seems hard. What are you doing to me? Oh, it's a proof. Ooh. We're supposed to... I guess I understand its formatting, but if I were to state the instructions for this, it would be consider, let me restate the instructions in my own fashion, okay? And so y1 is x over 1 plus x squared, yeah? And y2 equals inverse tangent, all right? Oh, and y3 equals to x. Great. And this on the closed interval from 0 to 10. All right. And we're supposed to prove x over 1 plus x squared is less than inverse tangent of x is less than x for x greater than 0. Now, the graph part is really optional. The problem here is, I mean, essentially that graph part is like, hey, it's helpful if you look at that. It might give you some sense of what you're doing. The actual problem is this right here. Okay. So how do we establish inequalities like that? You guys, I mean, how would you do it? Do you have any ideas? Let me suggest an idea. If I think of f of x as being x over 1 plus x squared minus inverse tangent of x, right? The question is then, what happens if we, so I'm trying to think of how to, what's the right way to argue this for you guys? I'm thinking if I look at the rates of change of these functions, I can show that the rate of change, basically, I believe I can argue that this increases faster than that, and that increases faster than that. Okay, so let me just get to that point. What would that mean? So let me just say that that's this. Well, this one's easiest. I'll start with the easy one. What's h prime of x? 1, right? What's g prime of x? Worked this out the other day, right? 1 plus x squared, right? And what's this say? What's the derivative of f with that f? Quotient rule, right? So that's 1 times 1 plus x squared minus x times 2x divided by 1 plus x squared squared, parentheses, important. So that actually is what? That's 1 minus x squared, right? Divided by 1 plus x squared squared. I'm not sure this is like the most convincing proof yet, guys. But you know, geometrically, do you understand why I'm saying that would give you some kind of proof? Suppose you have 3 functions, right? And they start out at this point. But then you look at the graph of one, you look at the graph of the other, you look at the graph of the third one. I'm arguing that this would be like y equals f of x. This would be like y equals g of x. And apparently I can't draw a line. Here, let me try to do that one right, at least. This would be like y equals to x, right? See, because if this one's always increasing at a faster rate, it's always lifting up off the graph of the other two, which means they stay in that order. If you can find a point, right, where f is smaller than g and g is smaller than, excuse me, if you can find a point where g is smaller than f and where h is smaller than g, and they're functions which the rates of change are also so ranked, it stands to reason graphically that they must continue in that fashion. It's not a good proof for your math class, but like pure math class, but it is a kind of proof here. So is it, I mean, it's clear to me that this, for x greater than 0, the rate of change of h is larger than the rate of change than g, right? 1 over 1 plus x squared at its largest is 1, right? And how about this one? For x positive, is it clear that that is smaller than this? Is it clear that this is greater than 1 minus x squared over 1 plus x squared squared for x greater than 0? I think it's clear because if we start out without squaring it, right? If we just subtract x squared from upstairs, we've made the numerator smaller, right? That gives me one inequality. And then if I make the denominator larger, that makes it smaller still, right? Assuming that x is what? I guess I do assume that x is, well, if x is very large, then anyway. I'm not sure what's a good way to do this for you guys in here. This is a problem I probably should stop and think about for like 20 minutes without trying to explain it. Yeah.
How come all these things squared again? Did you not cancel out 1 over 1 plus x squared?
It's unfortunately 1 minus x squared upstairs. Was it 1 plus x squared?
Now it's like 1 times 1 plus x squared minus x. Like the f of x up there. Yeah, how'd you from that to there, the bottom? When that big is 1 plus x squared? No, f of x, f prime of x. Maybe I'm confused on
F prime of x has got 1 plus x squared squared in the denominator because the,
there to there.
which there?
The
The numerator of f prime of x, how you get from the first numerator to the second numerator.
Oh, from here to here?
yeah.
It's because I've got 1 plus x squared minus 2x squared. So that's 1 minus 2 is minus 1. Oh, yeah, that I can answer. It's just algebra. I mean, this is minus 2x squared plus x squared, so net of minus x squared. Yeah. Anyway, let me, let's see here.
We maybe use the average value theorem, so integrate each of those and see what the average value is over that interval.
The average value theorem. I don't know if I know that one.
Or maybe it's the mean value theorem.
Oh, mean value theorem.
1 over b minus a times
Yeah, I think that would be a path towards a more serious solution to this. But I think, in short, I think this is a somewhat subtle problem. To like give a full answer to it would take me a while. But, I mean, the other game I could play would be to try to look at the difference and show that the derivative of those is always positive, which would show that the function's increasing, and then I think it would give me the necessary inequalities as well. But yeah.
Would it be possible to treat 1 minus x squared as a difference of squares?
Yeah, but I mean, sure, no complaints there. Absolutely none. But unfortunately, I've got 1 plus x squared downstairs. That was
1 plus x.
no 1 plus x. 1 plus x, unfortunately. I mean, it factors. Let's say x plus 1. That's the square root of x. Do we have x squared or x squared? 1 plus x squared plus 1. I mean, that's x plus I times x minus I. But I'm assuming that's a path we don't want to go down in here. So I'm going to move on. I would like for you to think through it and try to come to an argument for yourself. I mean, maybe it's just graphical. That's a good like first order solution, is just graph these and say if you look at the graph, it's clear that that inequality is met. But, you know, here, for example, if I take inverse tangent of x minus x, and I say that that's, let's say, script f of x, right? Then f prime of x is what? 1 over 1 plus x squared minus 1, right? In that, we can make a common denominator of 1 minus 1 plus x squared over 1 plus x squared, right? And then, I'm just trying to pick on one part of the problem to be more precise here. So that would be what? That's minus x squared over 1 plus x squared, right? So my question then is, where does f Where is f increasing? Where is it decreasing? What's the nature of this script f? If I set this equal to 0, does it have any critical points? The only way we can get that to be 0 is have what? X equal to 0, right? The numerator is only 0 if we plug in 0, and the denominator, that doesn't even, it behaves everywhere. So that shows me, in fact, you can look at this expression. This is pretty clear that f prime of x is less than 0 for x in the reals. Well, less than or equal to 0. Let's say it's less than 0 for x positive, right? So what does that mean? That means that f is increasing, right? Does that help us? Oh, I'm sorry. I said, you're disagreeing with me because I somehow got that the derivative of this function is negative, so the function's increasing. No. We have that the script f is what? Decreasing, right? What does it mean? So this shows that this is a decreasing function, right? What does this function decreasing mean? Yeah. Doesn't that say something about the relation between inverse tangent x and x?
X is greater than inverse tangent.
Yeah. Anyway, I'm going to go back to my original comment, which is, let me think about it further. If I can find something more constructive to say to you guys, I'll say it. But otherwise, I mean, for our purposes at the moment, it's fine if you just look at a graph and say, well, the graph indicates this inequality. All right. I do think there's something, what you said using the mean value theorem is probably a way you could come up with a precise argument. Yeah. Not unreasonable. Are there other homework questions? You guys are trying to stump me on all the hard ones. Mission accomplished. Let's see here. Which one?
Section 5.9, number 14.
5.9, number 14. Sorry, I can't say anything more insightful here today. It just didn't happen. Sometimes it happens, sometimes it doesn't. Let's see here. So you're supposed to show that cosh x plus cosh y is 2 times that cosh. And I mean, so the way I would do this is I would start on the right-hand side of the identity and just work it out. It should just follow it out.
First, we're on the right side this time.
I would, yes, start on the right side. If you start on the left side, you have to somehow imagine x plus or minus y appearing from nowhere. So unless you're really good at adding 0, starting on the left-hand side will make it super difficult. You start on the left side? There you go. So there. See, I have been helpful now without writing anything for this one. I feel like my day is better now. Yeah, start with that. What I was hoping for here, this would be an interesting exploration of graphing with calculus and the ideas of increase and decrease as they relate to inequality. That's what I was hoping for when I assigned this problem. Maybe it's too hard. I don't know. Other questions? Yeah.
Back to that problem. This might be stupid, but do the 2's cancel out or no?
Are we talking about the 14?
Yeah.
No, those are all those 2's, there's no cancellation of 2's. Those 2's are real. For example, well, no, I just, if I start trying to explain in words why that's true. But really, just start with the right-hand side and work your way to the left. It should be relatively straightforward. Any other questions? All right, so So our next integration technique is what's known as partial fractions. So partial fractions is fundamental, and it's a really important tool to have in your arsenal, so to speak. I will give you the big idea of it before I do examples. All right, so partial fractions, the idea is this. Given, P of x over Q of x, all right? If you want to integrate this, you can rewrite this as some polynomial, let's say f of x plus the remainder of x over Q of x. So first of all, and we've already seen this in examples today, if you have an improper rational function, in other words, if the degree of the numerator is larger than the degree or equal to the degree of the denominator, you can use long division to split off a polynomial piece. So the polynomial piece here I'm talking about is f of x. So here, P of x and Q of x, polynomials. I assume you know what a polynomial is. All right. So that's move number one. We can split that off. And then Q of x factors into products of the, either things like x minus, let's say, x naught to some power possibly, or x minus alpha squared plus beta squared to some power, let's say, I don't know, I need some other letter. It doesn't matter. Let me call it m again. What I'm trying to tell you is any polynomial can be factored into a product of linear factors and irreducible quadratic factors possibly repeated, right? So partial fractions, partial fractal decomposition says something like this. If I've got stuff, well, let me be more precise. S of x. Oh, I guess I called it r, didn't I? So if I've got like r of x divided by, let's say, x minus x1 to the m1, x minus x2 to the m2, and so forth and so on. And then I've got like x minus alpha 1 squared plus beta 1 squared to the, let's say, n1. And so forth. And I'm being deliberately a little bit vague here. Then there is a way of rewriting this thing as a sum of what I call basic rational functions. So for this setup, it looks something like this. I have a over x minus x1 to the m1 plus b over x minus x1 to the m1 minus 1. And so forth and so on until you've got, did I say A? I should number these so we can keep track. Let's call this A1. Let's call this thing A2. Da-da-da. A sub M1 over x minus x1. All of these terms in the partial fractions decomposition are coming just from this first factor in the denominator. This guy, producing all of these guys, right? Then you'd have similar terms for the x minus x2. I won't even write them out because I'm going to look at I'm going to look at smaller examples that'll make the pattern more clear to you. But then this quadratic term, what it does is it produces terms like, let's say, b1 plus c1 times x minus alpha over x minus alpha 1, that's an alpha 1, x minus alpha 1 squared plus beta 1 squared to the n1. And then plus b2 plus c2 x minus alpha 1 over x minus alpha 1 quantity squared plus beta 1 squared to the n1 minus 1. And this continues until you finally get to the lowest term, which would be b sub, let's say, n1 plus c sub n1, x minus alpha 1 over x minus alpha 1 quantity squared plus beta 1 squared. So for every term you have in the denominator, it spits out these terms in the partial fractions decomposition. All right? Let me be less vague. Let me try to expand on this with some very specific and lower dimensional examples, if you will. For example, in fact, this one example probably would do just as well as what I wrote in blue. So what's the partial fractions decomposition for this rational function? So first of all, you have to factor the denominator, and you got to make sure you put together like factors. If you've got different factors that are part of the same kind of factor, you need to collect them. That's not a problem here because x minus 2 is not x plus 1, is not x squared plus 4, right? And this over here, what's this? That's x plus 2 squared plus 1, right? So the two ones I have on the right there, those are irreducible quadratics. Sometimes you call them prime polynomials. On the other hand, the first two, these are linear or repeated linear factors. Okay? So here's the partial fractions decomposition we get from that. We write down a over x minus 2 squared plus b over x minus 2. That takes care of the first term. Use some color code in here. That's from this guy. Then plus c over x plus 1 plus, and that's all I need to take care of this guy. Now that x squared plus 4, to take care of that, I need a d plus ex. That'll do just fine. X squared plus 4. All right. And then finally the irreducible quadratic squared. That's going to produce a few more terms. That's going to produce f plus g times x plus 2 over x plus 2 squared plus 1 quantity squared plus h plus I times x plus 2 divided by x plus 2 quantity squared plus 1. No square on this one. That's it. That's what I'm trying to communicate in my abstract blue equation above. It's that for every repeated linear factor, if the repeated linear factor appears with a 10th power, it produces 10 terms. All right? Ranging from power 1 to power 10. If it's an irreducible quadratic, it produces also, as many, it produces more terms in some sense, right? I mean, well, let's see here. What else can I tell you? How many letters are there here? We got A, B, C, D, E, F, G, H, I. I equals 9 in the alphabet code, right? J is 10, I happen to know. What's the degree of the denominator here? 2, 3, 5. That's a quartic. That brings us to 9. So this is another